This one's nice because it's very similar to the one we've already done. Just like we did with an example of a fraction, if I have x over 2 equals 17 over 2, since the bases are the same, that means our numerators, denominators, our numerators must also be the same. Well, the same thing happens here. Look, I have a log 7 there, which now means that what's inside that log must be the same. So when I'm solving here, I'm effectively ignoring the log of both sides and just bringing down the 3x minus 1 and the 2x plus 1. What did I do? Because they are the same log, the insides have to be the same too. Now I'm going to isolate by subtracting 2x from both sides and adding 1. And here's my result. I'm going to check it real quick just by plugging things in. So when I plug in a 3 here, I get 9 minus 1, so I do get the 8. And here I get 6 plus 2, which is also 8. I don't even need to evaluate this. Look, it's the exact same on both sides. I'm done. The check is correct. The point of the check is not to get to a number necessarily. The point of it is to get both sides to be the same. And in this case, they are. So I've done the check there. Let's take a gander at part B as here. And what we're going to do here is sometimes we have to determine what properties to use or how to solve. Notice I have 2 logs. So what does that mean? If I can condense the log, so remember that skill that we spent on last week? If we can condense the log into one log, then I can probably take my skills that I just did. So notice what I have here. I have an x, I have a 4, and they're separated by a minus. The logs are being subtracted. So when I bring down the single log, the x divided by the 4, like so. Notice I don't divide by log 4, only one log. That's the point of the condensing. Great, now all of that equals 3. Now I can rewrite this, and I'm going to write it just there, just to remember. Well, you don't have to write that 10, but just to remember, if I were to rewrite like this, 10 to the 3 is equal to this fraction. Great. Now I'm in a position where I can just solve it like I would in normal everyday life. This one's 1,000, 10 cubed, and this is still x over 4. Now we multiply both sides by 4, and the result is 4,000 equals x. And what I did here was isolate my variable. So I had to do 2 things that were log related. Number 1, I noticed I had more than one log, so I had all the logs on one side and condensed it to a single log. Then I got rid of the log by effectively exponentiating both sides or just by rewriting it into exponent form. Now I'm in a position to get x by itself, and I do that with my normal skills. In this next problem, we've got options, so I'm actually going to walk through both of them here. And notice, as one of you said, all we have to do is rewrite that. So I'm going to say log of x squared equals 2. Now from here, you can recall, you don't have to write this, but just for memory's sake, that's a 10. So now I can rewrite it to be 10 squared. This right here, squared, is equal to this whole piece right there, x squared. And then you notice, you say, hey, wait a tick. They're both squared. They're both squared. Now it turns out, actually, mathematically, this was what happens. I do want to write out, we have 100. We get x squared. So when we do square root both sides, technically you have 2 answers, a plus or minus 10. So you need to check to make sure that both of those are actual answers. The negative 10 might not work. The positive 10 might not work. So mathematically, we get 2 answers, so you are going to want to check that. However, notice that some of you noticed right here, oh look, since the exponents are the same, and let me correct that so it looks more like a 2, the exponents are the same, the bases must also be the same. And you're absolutely right, x must be 10. But notice mathematically it also could be negative 10. So you do have to check that to double check. Now I want to see, what else could we have done? What else could we have done? Did I have to relocate that? And the answer is no. I could have divided both sides. So what happens when I divide both sides by 2? I end up with 1. Why? What did I do? Divide here by 2, divide here by 2. Now I rewrite like I did there, so 10 to the 1 power is x. Oh, look, there's no square involved. X is only 10. So notice that if I were to incorporate that square, my guess is that the negative 10 is actually extraneous. So I'm just going to write that over here with a check for the negative 10. I think negative 10 is extraneous, meaning it's too much. So 2 times the log of negative 10 equals 2. Now, log of negative 10, how do I simplify that? Remember, that's a 10. The question we're asking here, not with this 2, not with this 2, but just with this right here. 10 to some power gives me a negative number. 10 to some power gives me a negative 10. And we can't do that. Remember that the exponents do not create a negative in the front, even if the exponent were negative. Just remember, if the exponent were negative, it only makes it a fraction. It doesn't actually convert and make it a negative in the front. So in this case right here, it can't be done. So negative 10 is not an option. So when I do finally commit to an answer, notice 10 over there. The reason that I can suspect that there is an extraneous solution here is because my initial problem doesn't have a square. My initial problem can be interpreted as a square, but the initial problem is just 1x. That's it, just x. There's no other exponent. So in introducing this square, I've now effectively introduced an answer that mathematically works in one place, but not in another. So as we look at letter D, we're going to condense. How do I know I can condense? Because I have both of these are logs. They're common logs, so the base is 10. So I have to take this x plus 21 and the x and multiply them together. So when I bring down the log, my new inside is going to be x squared plus 21x, like this. All that equals 2 because the right side doesn't change. Again, you don't need to write this, but the common log has a 10 there. So I'm going to rewrite this to be 10 squared is equal to x squared plus 21x. And now we start to think, oh, this is a quadratic. So I need to isolate, put this in standard form and then solve using one of my mad skills. So I'm going to make that equal to 0 just by subtracting 100 from both sides, plus 21x minus 100. So at this stage, I ask myself, maybe Snowflake will work. I just don't know. So I try something. Maybe I can solve by graphing. Maybe I can solve by quadratic formula, completing the square. I'm not going to complete the square here because that's odd. If it were even, it would be an easier situation. I don't know if the factors of negative 100 add up to 21, but we'll see. So my guess is probably 25, right? 25 and 4. So let's see. I put the negative 100 aquí, and the x is there, and the positive 21 there. Oh, so positive 25, negative 4, because 4 quarters is $1, and there we go. So now notice what we have. Remember, from this stage, we can just take the opposites there to get the answers. So I'm going to skip the zero product property and jump to the negative 25 and the positive 4. Now what we have to do is just check. Do both of these work? Do these work? So is x negative 25 or is x going to be positive 4? So go ahead and just take a moment to check those. So when you log this one right here, notice, or substitute in, sorry, we have a log with a negative inside, so that's just not going to work at all. So that's just, it can't work. So clearly that first one is not going to work. So here I substituted in to get 25 there and 4 there. You're going to have to do change of base for this one and change of base for this one. How do you do that? Well, remember there's a 10 there and there's a 10 there. So in your calculator, you have to say this. Log of 25, well, actually, you don't even need to. Duh, no change of base, because it's already common log. So you just say log of 25, write that down, plus the log of 4, write that down. This is approximately 1.4 here. This is approximately 0.6. And then the 2 equals the 2. On my calculator, it was more accurate, and it did give me the exactly equal, so that's why I stuck with the exactly equal right here, even though technically this side is an approximation until it gets to this here. The last thing we want to look at is an application. Again, not where you're going to use it, but just showing you how it is used. By the way, so this equation, and you don't need to know where this came from, but that's the equation. I'll give you a hint. It's 1% interest over a certain number of years, and they start with $281 or people. So that's not interest, that's the growth rate for the population. So this equation is a model for the population of the United States Y in millions of people. So 281 million people in the United States approximately in the year 2000. So X years, so that X up there tells you how many years later. So in 2016, et cetera. So estimate when the United States will reach $400 million. So I have to take this and substitute it there. So we just want to know, according to the general population growth, when will it reach how many years after the year 2000? Now, models are models. They're not perfect. This could describe just 10 years of population growth, or it could describe 400 years. Generally speaking, the models are only models. They have to be adjusted. So I'm going to isolate the power there by dividing both sides by 281. So then I get 1.01 to the x power, to the unknown power. And I'm going to change that to an approximate right now. 1.4235. I'm going to round it out to pretty far, just because log and exponents also do that. In fact, I'm not even going to clear that from my calculator. Just keep it there. Now when I reconfigure this, I can now write this. So the 1.01 is my base of 1.4235 is approximately equal to x. Now this is change of base formula. The change of base formula, and I'll write it out, but you don't have to write this, is I put the 1.4235 on top with that log, and down below, it's the log of the 1.01. So after I do change of base, x is approximately 35.49. But I'm not answering the question yet. I want to go back to the question and make sure I answered it. Estimate when the United States population will reach 400 million people. So that's not my answer. My answer is in 2035 to 2036. So in 20 years from now, we could be at 400 million people.